Okay, so that's what I wanted to mention to you, and this ultimately is an extremely important method if you have numerical stiffness. If you're trying to do this, and you got fourth derivatives, fifth derivatives, sixth derivatives, and you're trying to just do it straight up like what we're doing in it, you are, as I said, 3 order magnitude difference in time step. This is huge. Okay? The computers now, today, I certainly would have been able to do this, just throw it on MATLAB and wait, because it's so much faster than that stupid 286. However, by the way, at the end of grad school, we just bought a 386. It was so sweet. 100 more. All right. So this is the kind of thing that you start thinking about, and it's very important that you are aware of it, because if you have a problem with numerical stiffness, you've got to figure out a way to deal with it besides just, I'll just wait longer. It's not a smart move. Okay. Here's what I'm planning to do the remaining 20 minutes of class. It's a very exciting part of the lecture. We're going to have computational smackdown. Okay? I know, exciting. You guys have like front row seats, live performance. Everybody else can watch it on YouTube, but it's never as good as like in-person smackdown. You're going to hear all the blow by blow. Okay? And in particular, you guys know what SmackDown is, right? That's the big Thursday night wrestling, big time wrestling, SmackDown. Okay, if you don't, now you do. Okay? So, partly entertainment, partly fun, partly just, you know, pinning together giants, smacking each other down. Okay, so what is this computational smackdown about? It is when you go to evaluate a routine, we've now learned finite difference, spectral. What are you going to use? Part of the point of this class is to give you the skill set that you don't just go, well, I have this code written, I'll just use it. No. For anything you do, you better have an evaluation and a criteria of why you're using what you're using. Period. Okay? So this is what this is going to be about. And part of what I want to set up for you is when we think about this, we're going to really be talking about spectral versus finite difference. Okay? What are the evaluation criteria? And let's put them head to head. See what happens. Okay? You guys ready? All right. I'm not sure if everybody's ready for SmackDown. I know it's a Monday. Usually we save these things for Saturday nights. But I figured you might not show up on Saturday night if I had SmackDown right here in this class. Because, you know, it's hot, you know. Probably just because it's Thanksgiving weekend, you're out of town. But otherwise, I'm sure you would come. All right. Let me get a better pen here. All right. So first, evaluation criteria. Number 1, or A. Accuracy. Okay? You have to make a judgment about accuracy. And what we want to do is evaluate. What is the accuracy like for finite difference? What is the accuracy like for spectral? Finite difference, you get to pick. Right? You can pick a, you know, how's my scheme? Delta x squared, or order delta x to the 4th, or whatever scheme you want to do. Right? It's always algebraic. You know, you use a certain number of neighbors. The more neighbors you use, the higher accuracy you can get out of this thing. But it's algebraic here. So it's rarely do you use that much higher than delta x to the 4th, because it's also more costly for implementation. Use more points. What about spectral? You just drop this term on you. Beyond all orders. That's right. Methods without borders.
It doesn't mean exact. It means just more exact.
Yeah, it just delta x to the... It's not algebraic. It's exponentially accurate. So you say that it's beyond all orders just means that. It's not algebraic. And effectively what that means to you is this thing dominates accuracy over this thing. And we've already played around with this, right? Did I do a derivative comparison where I think I, right? So if you do look at the finite difference in the spectral computation of derivative, you find that this thing just sticks on the line. This one here, it falls off pretty quick. Okay? So when you start going round one, who are we going to give this to? I know. Don't be shy. We know who took round one. Dang, that was like a... So we're going to start drawing up here just to keep this interesting. Okay. And first of all, he pulls out the forearm. Okay? And he has to flex his muscle when he does this because he's showing off right now. Okay? And this guy's took one in the head. I know. All right. But don't worry, that was in his action, right? Showing, movement. Okay. Round one. Boom! Walks around the ring. As you should if you're just dominating like this. Okay. What else are we going to evaluate on? Shh, not yet. We have to do this fight in the right order. Implementation. So when you do an implementation, you start evaluating how hard is it to implement, let's say, finite difference versus spectral. So let's talk about what each one does. In finite difference, your big thing is the construction of matrices. You remember constructing matrix A? Remember kind of getting it like, oh, geez, where's those ones? I got to slide this down. Okay? Now, once you get them, it's trivial, right? But it wasn't like so clear at the beginning that constructing matrix A was that easy to do, right? Especially you got to go to 2D. Now, we did learn the cron command, right? And that was pretty powerful. So, but still, the construction of matrices is your biggest deal here. And that's really the highest cost you pay, is that you've got to get those matrices, the A matrix, the B matrix, C matrix, etc. Spectral, we didn't have to do much, actually. The biggest thing in spectral is you have to remember, am I in the Fourier domain or am I not? Shoot, if I'm going to use FFT2, I better be a square matrix. Right? You have to do accounting. Okay? Am I in the Fourier domain? Right? You have to figure out, and you keep going back and forth, right? You go into the Fourier domain, you come back out of the Fourier domain, go into the Fourier domain, come back out of the Fourier domain, and you better understand when you go in and when you go out. To some extent, you say, well, okay, I don't even have to get a matrix right. Derivatives are trivial. IK, that's easy. Just that I have to keep track. So you might say here that maybe there's no winner. This is just about a personal choice. Okay? So over here, in our fight, not much happens, round two. This guy's going around, stomping around on his feet. But he doesn't hit him again or anything.
Is there a difference in nonlinear terms?
No, not really. You know, multiply them all together, FFT. No advantage. So here we'd say stand still. Nobody really takes this round.